So now that we've given a high-level overview of what our program is, the Simple Search Stream program, let's take a look at visualizing one of its methods. This is the find words method. And we're going to use this particular example to illustrate how some stream stuff works. So the find words method is going to search for words in an input string. So we've created a word searcher which was associated with an input string which contains the lyrics to our Do Re Mi song. And now we're going to go ahead and see how we can find the words. And this example appears in the WordSearcher.java file that you can see here. So what we take is we take a list of strings, which is the words to find, like do, re, mi, fa, sol, la, ti, etc. And the first thing that we're going to do is we're going to convert that list of strings, or list of words, which are strings, into a stream. And it's a sequential stream, and that's super duper easy. So you just say words to find dot stream, and that converts the list into a stream. And that outputs a stream of words. And you can kind of see here, I've visualized this. So we start out with a list, and then we apply the stream, factory method operator, and that converts this into a stream of strings. Next, we're going to use the map method. And map is a very common, very important method. We'll talk more about map here in a minute. But map basically says, essentially, for every element in the input stream, apply a mapper function, which is called search for words. And what that will do, as the name suggests, it'll search for that. It'll search in the input stream to find any word that matches. So we get a stream of words to find, and we're going to search for each word in the input string. And if we get a match, if we find a matching word, what comes out now is a different type. So you can see so far we've gone from list of string to stream of string, but we still have string, and that's what the kind of gray squares are, just showing that's one type of string. Don't worry too much about the semantics of gray squares. But the main point here is when we go through this map operation, we convert the type from a stream of string to a stream of search results. And this will then illustrate or demonstrate what we find if we find a match. So anywhere there is a match, we'll get back the search result. And that's going to keep track of various things. It's going to keep track of where the item happened to be in the particular input string. So what index it appeared at, for example. And the number of times. It'll keep track of the number of times it appeared as well. Note the transformation of type that takes place here. Map is an interesting operation in that it can convert the value and or it can also convert the type. In this case, we convert the value and the type. So we end up with a stream of search results coming from map. And then the next thing we do in our little stream is we're going to run the stream of search results through a filter. And what the filter is going to do is it's only going to allow non-empty search results to continue. So if for some reason somebody searched for a word that was not in the input string, like they searched for the word foobar or whatever, that was not there, then that search result would be removed. We would not have an empty search result continue after filter. Now for this particular input, where we're searching for the words do, re, mi, fa, sol, la, ti, in the lyrics to the Do, Re, Mi song, there's always going to be a match. But imagine more broadly that we were searching for different keywords in either the same input or different input, and there wasn't always a match. In that case, we would have empty search results, and so they would get removed. And notice how filter only allows predicates that evaluate to true to continue. If the predicate evaluates to false, then it doesn't continue. So at least under some circumstances, you could have a situation where we would have the reduction in the number of input elements relative to the number of output elements. So you'd end up with fewer output elements for things that don't match. They don't get through the filter. I've always found that semantic of filter a little confusing, because usually when you think of filter, you think of something that stops something from going through. But this is something that allows things to go through if they match. Just the semantics. You just have to learn that. And then the last thing we do here is something called a terminal operation. And a terminal operation is going to take the stream that comes in, which in this case will be the stream of non-empty search results, and it will collect it into another data structure, into this case, into a collection. And terminal operations like collect do two things. The first thing that they do is they trigger the intermediate operation processing, which means that all the other stuff runs, all these other operations like pulling the data through from the source, doing the map, doing the filter, and so on. All that stuff takes place. And then we also go ahead and we collect the results into a list in this case, because we give something called there's a collector factory method that creates a collector, which in this case will collect these things as a list. And so we'll end up with a list of non-empty search results as the result of this particular stream. And we'll talk later about other kinds of collectors. There's toSet, there's toMap, grouping by, all kinds of other ways of collecting stuff. But this is a list. And a list can allow duplicates. Now, one thing I mentioned earlier, but this will give us a good chance to kind of talk about it in a bit more detail. So it looks from my visualization here as if the processing takes place from left to right, top to bottom. Like it does all the processing up here, and then it does all the processing of the next row, and then all the processing of the next row, and then all the processing of the next row, and so on. It looks like that, but that is in fact not how it works. The way it actually works is it starts with each element, and it goes left to right, top to bottom. So it'll take the first element and do some processing. Second element, do some processing. Third element, do some processing. And the reason that it does it that way, two main reasons. One, it's much more efficient, especially with respect to concurrent or parallel processing, as we'll talk about later. And that has to do with something called essentially cache affinity and integrated layer processing and other cool things like that. And then the second reason it does it is because this way of doing things supports so-called short circuit operations. This particular stream does not have any short circuit operations, but we will talk about ones that do. And so the reason that things work from left to right, top to bottom, as opposed to top to bottom, left to right, is that it allows us to be able to support better efficiency with respect to caching and integrated layer processing, caching being things like processor cache, multi-core caches. And it also ensures that short circuit operations work effectively and finish just as soon as they possibly can. So that's the end of the visualization of the find words method. And we'll come back, of course, and talk about lots of other things and talk about the operators like map and find and factory methods and collect and all kinds of much more detail here shortly. But this is just kind of giving you the big picture view. And most streams programs look something like this.